Well, good morning, everybody. This is Mathman here, and we finally are at a point where we can take a look at integration. And we're introducing it here in several different ways. The first way is as antiderivatives, which isn't really the best way to introduce it, but it gives you the concept that it's really the inverse operation to taking a derivative. As a derivative is going down in order, let's say with a polynomial, the order or magnitude of the equation or polynomial reduces, and in integration it increases proportionately, and there's a analog rule to the power rule for derivatives with integration. When you integrate a polynomial function, it increases in order of magnitude by power of 1. And so we go through that, and then we take a look at integration as a from a different perspective, like derivatives have various interpretations. For example, the derivative of a function is considered the velocity, and then the second derivative is considered the acceleration. Well, with integration, you can take a look at a curve and take a look at 2 points on the curve in x and y direction, and integration is considered the area underneath the curve between those 2 points on the x-axis. So we look at it that way, and we look at approximating the area under the curve between 2 points on the x-axis using rectangles, and the smaller the difference in the base, or delta x, of the rectangle, the smaller the error of the estimate. And in fact, as delta x goes to 0, in the limit as delta x goes to 0, the area approximated by the rectangles under the curve becomes the area exactly. And then we take a look at setting up a problem rather than in a single dimension. We take a look at area from a different point of view rather than rectangles, which we introduce because when delta x goes to 0, that's basically the fundamental theorem of calculus. When you take delta x goes to 0, the area is an approximate, it becomes the exact area. Well, we take a look at problems from a different point of view, and we look at differential areas, dy, dx. They're infinitesimally small, and we sum up between limits of integration, and we set up the problem and sum up these infinitesimally small areas all the way from one limit all the way up to the other limit, and the problem becomes reduced to finding the limits of integration. So we introduce these concepts, and we actually these three concepts, and we summarize it in this film, this video, and we will take a look at integration in much greater detail in the next several videos. So this is really a bridge video just to introduce the concept of integration, what it is, how it can be looked at, and then we'll look at various applications, because it's a very important aspect of calculus. So this is Mathman, wishing you all the best. Now it's time for us to take a look at integration, and that's the second part of calculus. So when we have a function y equals f of x, we have some value or function that is in terms of the variable x. We'll just take a look at a polynomial. Let's say, we'll just give it a general polynomial, a x to the n plus b x to the n minus 1. And we want to take dy dx. So we go dy dx, which is equal to d dx of the polynomial and we end up using the power rule, a n x to the n minus 1 plus b times n minus 1 times x to the n minus 2. I'll make that minus sign a little bigger. I could have added c in there, and d dx of a constant is 0. So this is the power rule. But integration is the, well, some teachers call it the antiderivative. And so we can multiply across. We can say dy is equal to a n to the x to the n minus 1 plus b to the n minus 1 x to the n minus 2 dx. And then we can spread that across. dy equals a n x to the n minus 1 dx plus b to the n minus 1 x to the n minus 2 dx. And now we want to take the antiderivative. So the symbol that represents that is this elongated s equals, we can bring the a outside, n x to the n minus 1 dx plus b to the n minus 1 x to the n minus 2 dx. And now we have the power rule, or the analog to the power rule for integration. We have well, let's see how we can do this. Erase this little smudge here. Obviously, this is going to bring back y. And this is going to bring back a times n x to the n over n plus b times n minus 1 x to the n minus 1 over n minus 1 plus c. Because d dx of 0 is a c, we have the constant there. And the constant then is decided by initial conditions. So right now we're not going to worry about it. It's just a constant. And so we see, whoops, I forgot to choose my pen. We got y equals a x to the n plus b x to the n minus 1 plus c, which was our original function. At the very beginning. So you can see how taking the integral of the function is the anti-operation of a derivative. So if we had a function, if we have a function that starts out like this, dy dx equals x to the n, or let's say a x to the n. Then we go dy equals a x to the n dx. And then we say the integral of dy equals the integral of a is a constant, x to the n dx. But we're going up in power, so this is equal to a to the x to the n plus 1 over n plus 1. And we could say plus c. And this is y equals a x to the n plus 1 over n plus 1 plus c. Now, how do we know we did this right? Well, we take the derivative. dy dx equals a to the n plus 1 over n plus 1 x to the n plus 1 minus 1 plus d dx of c, which is 0. So we have dy dx equals a to the x to the n. So now we have a rule. And our rule is that if we have dy equals a x to the n dx, that's equal to a to the x to the n plus 1 over x, made a mistake there, sorry, n plus 1. And this is the integral analog to the power rule for derivatives. Derivatives go down and in order, and integrals go up in order. So in other words, if we have y, let's see, dy dx equals x to the third, let's say 4x to the third, then dy equals 4x to the third dx, and then we do our integration. Dy equals 4x to the third dx, and y equals 4 over 4 x to the fourth plus c. And that's the answer of using this rule. So you can see that why teachers like to call this the antiderivative, because it's opposite in its function to a derivative, and it's true in every case. And we had trigonometric functions. We have, let's see, did I pick a pen? Yes. Let's say y equals the cosine of theta, and dy d theta, as we know, is equal to the negative sine of theta. So dy equals negative sine theta d theta, and then we take the integral. Dy equals negative sine theta d theta. I keep forgetting the brackets. Then we end up with y equals cosine of theta plus c. We always just assume the c is there because when you take dy d theta of c is 0. So you can see it brings us back to the original function. So if we want to know what the integral of minus sine theta d theta, we know it's the cosine of theta. And we can use the same process to find derivatives or the integrals of cosine, tangents, and all the other trigonometric functions. And we will go through those. But there's one other way of looking at integrals that is more important, and I think we'll get looking at those right away. And that means that we're going to switch applications here for a minute. We're going to take a look at some Excel images that I created. So we'll stop at this point here, and we'll move to my, maybe before we do, maybe what we should do is this. Integration, like derivatives. Remember, a derivative, if you have, we have a function y equals f of x, and then we say dy dx equals dydx of f of x. That's equal to the velocity. Oops, that's not a very good L. Velocity of the original function. And then d squared y dx squared, the second derivative of d squared dx squared of f of x is equal to the acceleration. We had different interpretations, physical interpretations of the derivative, and that was a key thing to understand. Well, the same is true with integrals, and we'll take a look at it in just a second. As soon as I clear this board, I'll just use the eraser. Just take 1 second there. Okay, so what we're going to do is we're just going to look conceptually at, please forgive my lack of artistic prowess. We have an x and y axis, and we have some function f of x. Well, let's try something simple, like a parabola. F of x equals x squared. Well, if we integrate this function between two limits, let's say between 2 points on the x-axis, x1 and x2, we have up here x1 and y1, and we have x2. Whoops, I actually did this backwards, didn't I? All right. X2, y2, x1, y1. And we know that y2 equals x1 squared, or x2 squared. Y1 equals x1 squared. And what the integral between these 2 points, we call these the limits of integration. The limits of integration are this point, this point, this point, and this point. These are our limits of integration. And if we want to integrate that function between x1 and x2, we have x1, x2, x squared dx. That's equal to the area under the curve. So this is equal to integration is equal to the area under the curve between the limits of integration. And we're going to take a look at this more closely and how we come up with this interpretation. And there are various ways of looking at it. So, but that's a key element of understanding integration. It's a summing up of infinitesimal areas so that we sum up all those infinitesimal areas, an infinite number of them, and they give us the area under the curve between the 2 points or limits of integration that we're interested in. So now we can go to our Excel. Now, remember we said that the area under the curve, and this is a simple curve, y equals x squared. We said that we could approximate the area between 2 points or 2 limits of our integration. So on the x-axis, our limits of integration are between 2 and 4. And what we've created here are rectangles whose average value is given to be the point 1, 2, or not 1, 2, 3, and 4 on the x-axis, with a delta x being 1, so the base, or delta x, is 1, and you can see that this transition from this rectangle to that rectangle happens at 2.5, and we multiply that base times the height of that rectangle. We call it y average. So y average is taken to be the point at which we estimate the height of the rectangle. Here it's at 0.2, 0.3, and 0.4. And so if we take these 3 rectangles and multiply them by delta x, let's see, delta x times 4 is 4. And delta x times 9 is 9. And delta x times 16 is 16. And when we add those 3 rectangular areas up, we find that it comes out with an answer of 29. Okay, and I did a calculation in advance, and the true area under this curve between 2 and 4 is actually 18.667. It goes on actually indefinitely. That's an indefinite decimal point. It just goes on 0.66666 forever, but they truncated with a 7 rounding up. So you can see that using delta x as 1 doesn't give us a very accurate area or estimation of area. This is an approximate area under the curve. And you can see why we have that error, because some of the area under the curve is missing. It's not added in. And we have some area that's not under the curve that's being added in. And it turns out that the amount that's added in is larger than the area that's being left out. So that's why our value is bigger than the actual value. However, if we change the size of delta x, or the base of the rectangle, you can see it's at minus, or let's say 1.5 to 2.5, and here 2.5 to 3.5. The delta x is 1. If we shrink that down to delta x equals 5, or 0.5, half the width that we had before, we end up with 1, 2, 3, 4, 5 rectangles and a closer approximation, because the error of pieces of the rectangle that are added that aren't under the curve, and the pieces that are not being added, this white area, is smaller. That error is smaller than in the first chart, where the error was pretty big. When you look at these, what's being included and what's being excluded. So as we shrink the base of the rectangle, the approximate area becomes closer to the actual area. And if we continue to divide up the area into smaller and smaller rectangles, here the base of the rectangle is 0.25. I've been halving the delta x. We started with 1, then we went with 0.5, and then half of 0.5 is 0.25. And I have a problem here. I got this wrong. This is 18.667. And you can see it is closer. 21.19 is closer to 18. So in the previous it was 23. As we get smaller, the error becomes smaller, and the estimate becomes closer to the actual estimate. In this case, I halved 0.25 again to 0.125, and our area is 19, our estimated area is 19.92, which is getting pretty close to 18.667, which is the true area. And the thing is, if we continue to, I made a mistake, I moved that. Darn. There we go. If we continue to half the base of these rectangles, we could half it indefinitely. We can go on forever halving the base, and as we do so, we come to a closer and closer estimate of the true value under the curve. And here I have a table on this chart that shows the delta x, the approximate areas, starting out with delta x equals 1, and this is x exact, and I've done a comparison of the exact area compared to the different delta x's, and as you can see that as delta x gets smaller and smaller, the area becomes closer and closer. In fact, 1, 2, 3, 4, 5, 6 divisions of the original delta x gets us to an area of 18.8, and we're looking for 18.7. So you can see that we're less than 1% off of the exact value. And that error gets smaller and smaller as we continue to take delta x to a smaller and smaller division. And in fact, in the limit, as delta x goes to 0, the area that is estimated under the curve becomes exactly the area under the curve. So there's that's the fundamental theorem of calculus, that this limit, as delta x goes to 0, the area becomes exactly the area under the curve. And so that's basically the fundamental theorem of calculus. And that was first thought about in these terms, using rectangles, by Bernhard Riemann back in the middle 1800s, around the 1860s. And so that was the first time that anybody had put calculus on a theoretically sound basis. So that's basically it. It's not this tremendously complicated deal when you look at the fundamental theorem of calculus. So we'll go back to our drawing board, but I just wanted to show you this physical example because first off, my artistic abilities aren't so great, and so trying to hand draw these different charts would be a disaster. So at least you get the idea conceptually, and you can see that as the base of these rectangles gets smaller and smaller, the error becomes smaller and smaller, and it becomes more exacting as representing the area under the curve between the 2 points. So that's basically the fundamental theorem of calculus, that as delta x goes to 0, these rectangles exactly estimate. There are going to be an infinite number of these rectangles, by the way, and they will sum up exactly the area under the curve. Okay, so let's go back to the drawing board. When we look at this more from a mathematical point of view, this idea of the rectangles, and we have delta x under the x-axis. We got delta x, we're going to call it I, and we have our areas under the curve. You can see my artistic ability is not the world's greatest. So this point is xi, and this is yi average, which is equal to, in this case, fx equals x squared, or y equals x squared. Then this point will be xi and xi squared. and the area is yi, ai equals yi times xi, yi average. Delta xi, sorry about that, we'll erase that. It's because we're looking at delta x, delta xi, and so when we have a bunch of these rectangles and we have a bunch of them between a limit, so between I equals 1 to n, the area equals, or approximately equals, yi average delta xi. But then what we say is that as the limit of delta x goes to 0, then this sum of yi delta xi is exactly the area. That's basically what we're saying. It's no longer an approximation, it's the exact. Because delta x is going to 0. So again, that's basically the fundamental theorem of calculus. So let's take a look at it from a different point of view, and it's equivalent, and it's actually a better point of view than looking at it from rectangles. Now, rectangles, if you write a computer program or if you use Excel to estimate the integration, you can use that delta x approach and take very, very small delta x's, and it'll give you a very good approximation. I mean, that's what you call numerical analysis, when you approximate the exact result and you come very, very close because you've taken a very small delta x. Now, but here, why is my pen not working? All right, delta x between x2 and x1. And this is y equals x squared. It could be any f of x. Could be any polynomial function. This is your x-axis, and this is your y-axis. And then this point is x2, y2, and this point is x1, y1. And we want to look at the area here. What is that area between these 2 points of integration? Well, we could take a look at tiny areas, differential areas, and we could say that they're infinitesimally small, dx and dy, and that we're adding or summing these up all the way to the curve, between the curve and the axis. And basically, because these are infinitesimally small, we have an infinite number of them. So we're adding an infinite number of infinitesimal areas. And so what we write is dA equals dy dx. And that's basically one of these infinitesimally little areas. dy dx. And so now what we have to do is find the boundaries of integration. Well, if we integrate from the x-axis up to the curve, we're integrating in the y direction. So we're going to say a is equal to, now we're going to integrate from the x-axis, and the x-axis is 0, to the curve, x squared. And that's in the dy direction. In the x direction, we're going from x1 to x2 in the dx direction. So in the x direction, we're integrating between these 2 points here. And in the y direction, we're going from the x-axis to the y-axis. And that's basically all this is. We're finding the limits of integration, and we're summing up an infinite number of these differential areas. And so, when we carry out, this problem is already solved here. We just carry out the integration, and area equals, and we go x1 to x2, and we've got dy, which is y, x squared to 0 dx, and then we have x equals x1 to x2, x squared minus 0 dx. And now we just integrate in the x direction, and we know the power rule for the integration. We learned it just a few minutes ago, and that would be area equals x to the third over 3 between x2 and x1. So that's equal to 1/3 x2 to the third minus x1 to the third, and that's our answer right there. That's basically the way to think of integration, especially when you're thinking in 2 dimensions, like areas. Areas is 2 dimensions. Volumes, 3 dimensions. When you're thinking of areas, you think in terms of dy dx. And in volumes, we have we got dx, dy, dz. We got 3 dimensions. And that's dz, dy, and dx. So it just comes down to adding up these infinitesimally small areas or infinitesimally small volumes, and we are just looking for the bounds or the boundaries of integration, and that's it. So it's actually simpler than what mathematicians try to teach about trying to find areas in one dimension and volumes in one dimension. What they do is they call it the volume of revolution. It's so much easier to find the volume when you've written an infinitesimally small volume like that, and then try to find the limits of integration in the z, y, and x directions, and then calculate it that way. Because when you do this volume by rotation, it's not intuitive at all, not intuitive, and it's not easy. It's much easier to take a look at volumes using this approach, the infinitesimal volume. So we'll get into that. We'll take a look at that. But you could see that the thought process is much more logical in setting up an area problem this way in terms of dy dx, and then summing up these infinitesimally small areas between your limits of integration in both directions. And so at this point, we'll just leave it at that. We've essentially looked at an approximation method for integration. We looked at integration as being sort of an inverse function of derivatives. We call them antiderivatives. We looked at an approximation method using rectangles and how that leads to the fundamental theorem of calculus. And now we're looking at an approach using infinitesimal areas and infinitesimal volumes, and simply looking for the limits of integration. Basically, it's a logical process of setting up the problem. So we'll be going through a lot of these, and we will hopefully we hope that this is a better approach to integration than what math teachers normally give you. It's so much simpler once you've gotten this method down. It's so much simpler to set up a problem like this, because it's a thought process. It's critical thinking. It's thinking about what problem do you have and how do I set it up. And so we'll take a look at a number of these. We'll try and get plenty of practice so that you get the idea, that you catch on, and you can see that any other approach is completely useless, because once you've learned this approach here that we've looked at here, you will never go back to anything that a first-year calculus class will teach you. So we're just going to skip the extraneous junk, because it really isn't simpler. This is far more intuitive. I hope that this video has been helpful, and we'll take a look at integration in far greater detail in the next several videos.